Hello and welcome back. So this video is for class 12 and we will continue with the chapter of electromagnetic induction. So in the previous class we saw the Faraday's law and the Lenz's law. Now I know the Lenz's law might not have been very easy to grasp, but make sure that you read it again, okay, and you see the examples that were given on it. So that will make it much more easier. Today we will see the next topics. The first one that we will see is the concept of motional EMF. Okay, what do we mean by motional EMF? Let us see. So first of all, we are having a magnetic field, okay, that is represented by these X's. So we are having a magnetic field that is going inside, okay, and it is perpendicular to the board. Then we have a wire, okay, this rectangular shape that you are seeing, this is a wire, and we are having a rod that we have given the name of PQ. Okay, so we are having a rod PQ. So all together we get the shape PQRS. Right, and the rod is such that we can move this rod while it is in contact with this wire, okay, over this wire without any friction, right? And we want to see if we are doing this whether it will produce any kind of EMF. Okay, so let us see. So obviously the first question you would ask is, just by moving the rod, how can we get an EMF going through the rod? Okay, so here is the thing. So when you look at this rod, that is PQ, right? It is in contact with this wire, so we get an area PQRS, this entire area we are getting. And you can see that there is some magnetic field going over here, right? So when you are moving this rod, you can see as PQ will move towards to RS, what will happen is the area will go on decreasing. As the area will decrease, that means the magnetic flux in that PQRS is also going to decrease as the area of PQRS decreases. And as the magnetic flux decreases with time, that will mean we are going to get an EMF that is given to us by Faraday's law. Okay, so that is the reason why we will get some EMF going in PQ. So that is the thing. Okay, so now let us do this derivation. We will give some values to this. So let us say length of PQ, this length is equal to L. So obviously RS, this will also be L. Okay, and the distance from R to Q, let us say that is equal to small x. Okay. Then as I said, L is the length of this PQ, that is only with that part which is in contact with the wire. Now we are going to move PQ towards RS, okay, in this direction, let us say, and with a velocity of V. Okay, so we are moving PQ towards RS with velocity V. As this is happening, you will see that the area will go on decreasing, thereby the flux will also go on decreasing. Okay, so let us start. So now we know by the definition of magnetic flux that magnetic flux is equal to magnetic field multiplied by area. So let us say B is the magnetic field. How much will be the area? L into X. So B L X. Now in this case, the area vector and the magnetic field, they are parallel to each other. So theta is 0. So therefore cos 0 will be 1. So that is why we are not getting any theta value over here. Okay, so we will get magnetic flux as BLX. Let us call this equation number 1. Right. Now by Faraday's law, the EMF generated will be equal to E is equal to minus d phi B by dt, which is equal to, we can put it here, magnetic flux, the magnetic field is a constant, so we will get it minus B. This length, that is also a constant, so that will also come out. So we will get minus BL dx by dt. Correct? Now dx by dt, that is change of position with time, displacement upon time, and that is nothing but velocity. So we can write instead of dx by dt, we can replace it by the velocity. Since it is moving backwards, that is flux is decreasing, we will put dx by dt as minus v. Okay, so we will get this as, therefore E is equal to, as I said, BL will remain as it is, and minus dx by dt will put as the velocity v. So you will get EMF generated is equal to BLV, magnetic field into length multiplied by velocity. So that is what happens when you move a rod in a magnetic field. There will be an EMF set into it, which is given by BLV. Obviously you can see that if you increase the velocity, the EMF generated will be higher. Okay, if you decrease the velocity, means lower velocity, EMF will be lower. Now of course one question you will ask is, in what direction the EMF will go? That is, whether it will go from P to Q or Q to P. which is a positive. For that you can remember when we had seen the Lorentz force or the magnetic force. Okay, magnetic force that is on the charges of this rod, that is given by F is equal to Q into V cross B. Okay, so if we take V cross B, so V is this side, B is going inside, so V cross B pointing downwards. So actually the charges will go from P to Q. Okay, so I hope that was understood. Now next we are going to derive a formula for the power that is dissipated in this case. Okay, so again what is happening is rod PQ is moving towards RS. Because of that there is an EMF generated over here, and obviously if there is an EMF there will be an electric current. So we will assume that I is the current that is going through this loop. Okay, that will go through this entire loop PQ RS. Now we want to find out how much will be the power dissipated. Okay, so let us say that I is the current through that loop. So we can write I is equal to E upon R. Okay, where R is the resistance. We are going to assume that the resistance of that loop does not change. Now we know that E is equal to BLV from the previous derivation. So this we can write as I is equal to BLV upon R. Let us call this our first equation. Now that rod PQ, when it was moving, there will be a force that will be exerted on that rod. That force will be equal to I into L cross B. I hope you remember this was a previous we had seen this derivation. Okay, that when a rod is moved, okay, in a magnetic field there is a force that is exerted on it, on a current carrying rod. So I into L cross B. Now L cross B, the angle between them is 90 degrees, so therefore sin theta will be 1. So the magnitude of this force, okay, once again I will repeat. This is the force exerted on that rod PQ by the magnetic field. So F will be equal to I L B. Okay, because sin theta is 1. Then we can see, we can use equation number 1 in this equation. Okay, so we will replace I by BLV upon R. So we will get B into B will get B square. Okay, L into L will get L square. Then V divided by R. Okay, this is the force that is exerted on our rod. Let us call this equation number 2. Now, how much will be the power dissipated? To find the power dissipated, we can use the formula power is equal to F into V. Okay, I hope you remember this relation. In 11th class we had seen power is equal to work upon time. Okay, and then work is nothing but force into displacement. Okay, so displacement upon time, that will be velocity. So we can write power is equal to F into V. Okay, this was done in 11th class. So again, I don't want to repeat entirely. So power is equal to force into velocity. So force is how much? B square L square V by R. So therefore we will get this as B square L square V square upon R. Okay, that will be the amount of power that will be dissipated when you move the rod. Let us call this equation number 3. Okay, now there is one interesting relation you will see here. We know the Joule's law of heating. Okay, so this power that is required, this power that is converted into electrical energy, we can see that the same amount of power will be converted into thermal energy. How? By Joule's law of heating we know that the power required will be I square into R. Okay, how much is I? I was BLV upon R. So square of that multiplied by R, you will get B square L square V square. R square and this R will get cancelled. So we will get this as B square L square V square upon R, which is very similar to equation number 3. Okay, so that is nothing but the heating power. So we see that we put some power for moving the rod. That was mechanical work done. That was converted into electrical power. Electrical power is this. Okay, and the same amount of power you can see, you can find the same value by the Joule's law of heating as well. That is, that power can be converted into heat energy. Okay, so that is an interesting relation we see over here. Okay, now next we are going to talk about the concept of eddy currents. Okay, now this is a very wonderful, it's an application of the electromagnetic induction phenomena. Okay, so first let us talk about that effect and then we will see more about it. So here I have for you a magnetic field. Okay, so this is a very limited space in which we have put the magnetic field. Outside of this there is no magnetic field. Okay, only in this region we are having a magnetic field that is pointed inwards. And now you have to imagine this is a metallic plate. Okay, it is of course not metal. Okay, but you have to imagine that this is a metallic plate, not a ring, a complete plate. Now what we are going to do is we are going to swing this metallic plate between this magnetic field. Okay, in this manner. So now you can see the plate is swinging in and out of the magnetic field. First, when it is here, it is not experiencing any magnetic field. As it comes inside and slowly it enters the magnetic field, it moves around and then it comes back. Okay, so this is the situation that we are getting here. Okay, we have a plate that is moving in a magnetic field. Now when this happens, inside that metal plate, we get something called as the eddy currents. Okay, and because of those eddy currents, this metal plate will start to get heated up, and after some time it will actually stop swinging, it will come to a rest. Okay, so let us see what is that phenomena. So as I said, the phenomena we call as the phenomena of eddy currents. So what happens is, when that metal plate is outside, no magnetic field is there. As it is entering inside, what will happen is the magnetic flux will start to increase. Is that correct? As the plate is just entering the magnetic field, we'll get an increase in the magnetic field. Now we know that as there is a magnetic flux, there will be EMF, right? But because, as I said, this is a plate, right? The EMF that we get here is going to be little different than what we had seen previously, right? So when this plate is going inside, right, we can now find out the direction of EMF, right? We know because it is going inside, right? The direction of EMF is like this. The direction of flux is like this. That is clockwise for me. So EMF will be anti-clockwise. That is given to us by the Faraday's law and Lenz's law. So as the plate is going inside, the EMF that is generated will be anti-clockwise, and we will get an EMF like this. Okay, is right? So we will get an anti-clockwise EMF in that metal plate. Then while swinging, when it is moving in the magnetic field, no change. Correct? No flux changes there, so no EMF. Then when this plate is coming out of the field like this, okay, so when this metal plate, it is coming out of the field, what will happen? The flux will start to decrease. So direction of flux in this case is going to be like this. That is anti-clockwise. So definitely EMF will be clockwise. So it is coming, as it is coming outside, the flux that you will get will be clockwise now. Okay. So once again, when the metal plate enters when this plate will enter the field, the EMF is going to be anti-clockwise. As it goes out of the field, EMF will be clockwise. Okay, and these look like eddies. Now what are eddies? If you put your hand in water and just move your finger, you can see the water starts to swirl around. These are called as eddies. Okay, and this current that we get here, that is known as the eddy current. Okay, so this current that we are getting inside that metal plate, that is known as the eddy current. Okay, now what happens due to the eddy current? As I said, heat is generated inside the metal plate. Okay, and that is an undesirable effect that we want. For example, when we are driving our car, okay, in the car there are many moving parts, right? There are magnetic fields. So if there are eddy currents are there, the car parts might get damaged. So these undesirable eddy effects, we try to reduce them. How we can reduce them? This metal plate, if it is having holes inside it, the number of eddy currents will be reduced. Or if you have a comb-like structure, that means instead of having a complete plate, if we have a plate that is like this, right, which is having gaps inside, that can also help to reduce the eddy currents. Okay. So I hope you were able to get the idea of eddy currents from that simple demonstration. Now as I said, mostly eddy currents are undesirable, but we have managed to find some uses of it as well. Now first use, as I said, as this plate is moving to the magnetic field, it will come to a rest. So this is actually used in something called as electromagnetic breaking. Okay, so we can use eddy currents to stop a moving car, right? We set up eddy currents in the disc. So that is one application of it. Next, we use it in induction furnaces. As I said, if we have eddy currents, that can actually heat up the metal plate to a very high degree, and we can actually manage to melt that metal by producing eddy currents. And one of the best uses of eddy currents, nowadays we are not using it, we will have digital meters, but in the old days, if you had seen your power meter, okay, the electricity meter that we have, that would have a a rotating disc, right? It was made up of aluminium. So that rotating disc is nothing but it is working on eddy currents. Because of the current that we are getting in our house, eddy currents would be set up in that disc and it would start to rotate. So depending on the number of rotations, we would be able to understand how much power was utilized. Okay. Nowadays, instead of the disc, we are having digital meters. But even in some places, you can actually see that moving disc. So these are, and of course, galvanometers. We can design galvanometers based on eddy currents. Okay, so these are some of the applications of eddy currents. Okay, so now next we are going to see a new physical quantity, and that is called as inductance. And there are two types of inductance. We have either self-inductance or we have mutual inductance. Let us see them one by one. So consider we have two coils like this. Okay. If we pass an electric current from one coil, we know that the flux around this coil will change. Okay, and because of that, there will be induced EMF in the second coil. This is something we have discussed in the beginning of this chapter. Correct? So what you can say, let us say that the flux in this coil is 5, right? And there are n number of turns for this coil. Because of changes in the flux around this coil, there is a current I which is flowing through the other coil. Correct. So we can say that the flux that is the change in flux that is taking place is directly proportional to the electric current, right? So depending on the change in flux, the current is going to change. So this we write as N phi B directly proportional to I. Correct. This term, that is N phi B, N is the number of turns of that coil and phi B is the flux, okay, that is taking place. So this term we call as the flux linkage. Okay, and what we see, flux linkage is directly proportional to electric current. So depending upon how much the flux linkage is changing, the electric current will change. And you can see there is a sign of proportionality. To remove that sign of proportionality, we add a constant, and that constant is called as inductance. And as I said, there are two types of inductance. One is mutual, one is self. Here, because we are having two coils, the inductance here will be called as a mutual inductance. Okay, because change in one coil is causing a current in the other coil. The other type is called as self-inductance. What is self-inductance? You can take a single coil like this, having n number of turns, and we can pass a varying electric current through this coil. So if we pass a varying electric current, what that will do? That will change the flux for that coil. And for that same coil, there will be a back EMF setup. Okay, so in the same coil, flux is changing, and because of that, an EMF is getting developed. This will be called as self-inductance. Okay, so here we see a coil that is having n number of turns that is connected to an AC power supply. So now what is going to happen? Because of that AC supply, current in the coil will change. Because of the changing current, the flux around the coil will also change. Okay, and that is going to create an EMF. Okay, and the phenomena we will get here is called as self-inductance. So for this coil, you can write the relation, that is N phi B, that is the flux linkage, is directly proportional to I. Here this I stands for the induced current. Okay, this I is not the current that is sent by the AC supply. Okay, this I is the induced current that is due to the induced EMF. So we can write N phi B directly proportional to I, right? And now, as we said, to remove the sign of proportionality, we add a constant. So we will write this as N phi B is equal to capital L into I. This capital L is called as inductance, or more specifically self-inductance, right? So for this given coil, the self-inductance of that coil will be given by capital L, or you can write L is equal to N phi B by I. So L is a constant that will depend upon the dimensions of that coil, and it will depend upon how much is the flux linkage of that coil. Right? So we can write L is equal to N phi B upon I. Okay, and of course we can put the SI unit for it. That will be Tesla meter square per ampere. But it is given a special name, and that is Henry. Okay, it is named after the American scientist Henry, who discovered the phenomenon of electromagnetic induction. So the SI unit of inductance is Henry, right? Now we will derive some important formulae for self-inductance and mutual inductance. So once again, so this is the same coil through which we have connected an AC power supply, so that it is going to have a self-inductance. Remember, to have self-inductance you will need an AC supply. If you give a DC supply, you will not get any self-inductance because the current flowing is going to be constant. So you will need an AC supply for self-inductance. But anyways, so here is our coil. Let us say L is the length of the coil, R is the radius, okay, and capital N is the total number of turns of our coil. Okay, so with that we are going to start with our derivation. So what we are going to consider, that small n is the number of turns per unit length of the coil, so that capital N, the total number of turns, will be equal to small n into L. So remember this relation. Let us write this as equation number 1. Right. Now again we will start with this previous case, that is the flux linkage will directly be proportional to the induced current. So therefore we will get N phi B is equal to capital Li, where L is the self-inductance of the coil. This let us call equation number 2. Now we can figure out the left hand side of this equation very easily. Let us write it. So therefore we can write N phi B is equal to, how much is capital N? Capital N is equal to small n into N, right? How much is phi B? That is the flux. Flux, I am sure you remember, is magnetic field multiplied by area. Now for this coil, that is a solenoid basically, right? When we are seeing coil, it is basically a solenoid here. So for a solenoid, how much will be the magnetic field inside? I am sure you remember, magnetic field is going to be mu naught small n into capital I, correct? So mu naught Ni, that is the magnetic field inside, multiplied by A, that is the area. Here we need not calculate the area differently. So what do you get? N phi B is equal to this, which is equal to, so n into n, you will get n square. So let us write it like this, mu naught n square L into I into A. Okay, so this is the flux linkage. Let us write this as equation number 3. Now comparing equation 2 and 3, we will get, therefore Li is equal to mu naught n square L IA. Okay, I gets cancelled and therefore we get L, that is the self-inductance, is equal to mu naught n square L into A. Okay, so this is the formula we have got for the self-inductance of that solenoid. Of course, we have assumed that inside the solenoid there is air or there is vacuum, right? If there is a material that is having a relative permeability mu r that you have put inside that solenoid, this equation will get transformed as L is equal to mu r mu naught n square L into A, right? So this gives us a formula for self-inductance. You can see that the self-inductance of a coil will depend upon how many number of turns it is having, how much is the length and the area. So the physical dimensions of that particular solenoid will actually determine its self-inductance. Now another thing to remember about self-inductance. See, current is going in the same coil, right? And then there is a magnetic field being developed around it, which is actually opposing the current that you had started with, right? It is producing something called as a back EMF, right? So basically what happens, if a coil gets self-inductance, it is going to oppose the current, the original current that is actually going through it. So that is why for this EMF, one name is given, that is called as a back EMF. Okay, so I hope you understood the concept of self-inductance. Next we are going to talk about the concept of mutual inductance. Okay, so on your screen you can see we are having two coaxial solenoids. What is the meaning of coaxial? Both these solenoids, they are having a common axis and they are having the same length L. Okay, the solenoid inside, let us call it S1, and the one outside, let us call it S2. Okay, so this is the situation. we are going to pass current in both the solenoids, and then we are going to get mutual inductance. Because what will happen? Let us say we pass current through the outer solenoid S2, right? Because of that, the flux for the inside solenoid will change. Because the flux linkage will change, it is going to get some EMF. Okay, that is electromagnetic induction. So that is the phenomenon of mutual inductance. Okay, so I hope that diagram is clear to you. Now let us start with our derivations. So here is what we are assuming. Solenoid S1. Okay, it has got N1 number of turns per unit length. There is a current I1 going in solenoid S1, and it is going to have length L. Okay, then for solenoid, also the radius of solenoid 1 is R1. For solenoid 2, it will have number of turns per unit length N2. The current in solenoid 2 will be I2. Length will be L. Okay, notice that we are considering both solenoids to have same length, because if their lengths are not similar, this derivation will not be so simple. Okay, so for our convenience sake, we will consider both of them to have same length, and the radius is going to be R2. Doesn't really matter which is having a larger radius or smaller radius. For this consideration, we have considered S2 to have a larger radius. Okay, so now let us assume initially a current is going to pass from S2. Because of that, there is going to be induction in the coil S1. So you can say that flux linkage of coil S1, capital N1, phi 1. Okay, this is the flux in coil S1. N1 is the total number of turns in coil S1, is directly proportional to I2, the current in the second solenoid. Okay, making sense? I hope this is not too difficult to follow. So this is the proportionality you are getting. I2 is the current flowing, which is causing a flux linkage N1 phi 1. So then we'll remove the proportionality, we'll get N1 phi 1 equal to, now the constant we'll add is M12 multiplied by I2. What is M12? M12 is called as mutual inductance of S1 with respect to S2. Okay, so M2, this is the constant mutual inductance, and we have to specify M12, that is inductance of coil 1 with respect to coil 2. Fine, let us give this an equation now. We can call this equation number 1. Now, just as before, we are going to find the left hand side of this equation, that is N1 phi 1 equal to, how much is N1? Capital N1 is small n1 multiplied by L. Okay, number of turns per unit length multiplied by length. So this is capital N1. So capital N1 is small n1 into N. Phi 1, the flux for the coil that is inside. First, magnetic field. How much will be magnetic field? It will be mu naught N2 into I2. Making sense? Because this magnetic field is due to the coil that was outside. So I have to take mu naught into N2, the number of turns per unit length of the outer coil, multiplied by I2, the current going in the outer coil, multiplied by area. But area which you will take? Area you will take for the inner coil. How much will be the area? Pi R1 square. Okay, let us call this equation number 2. Now comparing equation 1 and equation 2, you can see LHS are the same, therefore RHS must be same. So this term M12 I2 equal to this entire term. What can you cancel? I2 you can cancel. So I2 gets cancelled, and therefore we can write, therefore M12, mutual inductance of coil 1 with respect to coil 2, is equal to, this is the same equation, I am just going to rearrange it so that it is easier to read. Mu naught, then we can take N1, N2, then we are left with L into pi R1 square. Let us call this equation number 3. So equation 3 gives mutual inductance of coil 1 with respect to coil 2, which is equal to mu naught N1 N2 L pi R1 square. Okay, so that is for the first coil with respect to second. Now let us try to find out M21, that is mutual inductance of second coil with respect to the first coil. So we will start our derivation just like before. Now we are going to pass an electric current through the inside coil through S1. I1 will go through S1. That will create a flux for coil S2. So you can write flux linkage for second coil directly proportional to I1. Flux linkage for second coil you will write as N2 phi2 is equal to M21 I1. Okay, I am sure now you have followed how this equation has been written. We will call this as equation number 4. Okay, again this we can find out the LHS. N2 phi2 will be equal to small n2 into L. Then how much will be the magnetic field inside? It will be mu naught N1 I1. Okay, because it is the current is going through the coil S1 multiplied by how much is the radius? Pi r1 square. Now you will notice we have not taken pi r2 square here. Why? Because the magnetic field is in the inside coil only, right? We cannot take pi r2 square. The magnetic field has not spread to that second coil. Okay, it is confined in that inner coil. Therefore, you will get pi r1 square only. Okay. So coming back, so this will be equal to so let us call this equation 5. Comparing equation 4 and 5. You can see the RHS is equal to RHS. So I1 you can cancel out, and therefore you can write M21 flux the mutual inductance of coil 2 with respect to coil 1 equal to, once again we are going to rearrange it and write it as mu naught N1 N2 L into pi r1 square. Let us call this equation number 6. And if you compare M21 and M12, you will notice both of them are exactly the same. So mutual inductance in coil 1 due to coil 2 is the same as mutual inductance in coil 2 due to coil 1. Now this looks very nice and very convenient. This has happened because we have taken the coils in such a manner that they are having the same lengths and they are coaxial. Otherwise, determining this would have been a very, very tough task. Okay, so this thing you have to keep in mind. If let us say the length of one coil had been shorter, okay, in that case there would have been a lot of inductance on the edges. We would not get such straightforward and simple equations.